Hello students, I am Sonu Kumar. Today, let me discuss about the Fraunhofer diffraction through a single slit. As we know that in the Fraunhofer diffraction, the light source and the screen are effectively at infinite distances from the diffraction elements or obstacle. Let me consider the light is coming from a source S and framed into the parallel beam of light rays are by using the convex lens. Now, this parallel beam of light rays, incident rays, normal on the slit AB of width D. The diagram for the Fraunhofer diffraction is in this way. We have a source, and the source is emitting light rays in all direction like this, and this is the wavefront for this light source S. This is a principal axis for the ray, and here we are drawing a screen y dash, y dash be the screen, and O be the center point. As according to the definition of the Fraunhofer diffraction, the source and screen both are infinite distance from the slit. Let the slit is AB, AB, and this distance are effectively large. So to produce a plane wave, we need two lens, one lens in between the source and the slit, named as L1 and L1 dash. It produces a parallel beam of light and and give a wavefront in the form of WW1, a plane wavefront. This is the plane wavefront. Plane wavefront, and a lens is also taken in between the slit and the screen because this distance is also effectively large. So to obtain a diffraction pattern at the slit, we need another lens, convex lens here. Convex lens here. This convex lens is named as L2, L2, L2 dash. And the rays are coming from this and reach at the point or at O and produce a central bright fringe. In the case of Fraunhofer diffraction, we get always central maxima, But in the case of Fresnel diffraction, either maybe a bright, central bright, or maybe a central dark. Now our point is to find out the maxima or minima at point P on the screen. Then this light rays go from A to P through the lens L2 like this. This point is considered as A dash and this is B dash. Let we draw a perpendicular on BB dash is K. Let's make an angle theta with the slit. So the light is reaching at the point P from A and from the point B have a path difference is BK. It have a path difference is BK. In the diffraction pattern, the central fringe is always bright. In the case of Fraunhofer diffraction, as I told you, on the other hand side, on the either side of this central maxima, alternate maxima and minima bands of the decreasing intensity observed. The analysis for the Fraunhofer diffraction through a single slit. For the analysis, let we take the half part of the diagram. This is the slit AB and we use here a lens to converge the rays on the screen. Here this is the screen YY dash and rays are coming from the source and this is the principal axis where we get the central maxima. Let me find out the maxima condition for maxima and minima at point P. This is the ray coming from A and B with a path difference BK, which is perpendicular on BB dash. To calculate the path difference of rays reaching at point P from A and B is calculated to draw a perpendicular on BB dash, which is AK, as it is considered that the width of the slit is very small. as compared to the aperture of the lens. So the rays are almost perpendicular to the screen, which are coming from A dash and B dash. So the rays EP and BP are equal due to small slit width. Due to small slit width, this width is considered as D. Let me calculate the path difference for this for the analysis from the triangle ABK. This we have the path difference is equal to D sine theta, and to find out the end to find out the diffraction pattern at P. we need phase difference of rays reaching at point P on the screen. Then the phase difference is 2 pi by lambda into path difference. Let if we consider the slit is assumed to be make up of a n number of slit. If consider the slit is make up of a n number of small slit, number of small slits, then the amplitude of the each secondary waves originating from this path will be equal. Then the amplitude of each small small slits will be equal, and the path difference between the two successive waves will be equal to, and the path difference difference between any two successive wave it will be equal to the path difference. Total path difference is divided by 1 by n. This is the total path difference. 2d sine theta, and this is the total phase difference, and let we divide this with n. We get the phase difference between two successive small slip small slits. Thus the resultant in the direction of theta, due to the superposition of such n number of secondary waves, and the resultant is denoted with r. And how can we calculate? This can be calculated with the help of resultant of n harmonics waves. R is calculated with e e sine theta, sorry, e sine n dash divided by sine just divided by 2. This is the formula of resultant of n harmonic waves. N harmonic waves. Let me put the values of dash, this delta dash is equal to r is equal to a sine n 2 pi by lambda into d sine theta divided by 2, this divided by sine delta dash, this is equal to 1 by n 2 pi lambda multiply d sine theta divided by 2. After the solution of this equation, we get e sine pi d sine theta divided by lambda, the whole divided by sine pi d sine theta divided by n lambda. This is the resultant of the n number of slits For the solution of this equation, let me consider some assumptions here. Pi d sin theta divided by lambda is equal to alpha. Then what will happen? Then we get r is equal to e sin alpha and divide by sin alpha by n. Again, the alpha by n is very small, so sin alpha by n is a process to alpha by n, which is due to a very small angle. Then sin theta is equal to theta. Let me put the equation, this value in the previous value. Then r is equal to, then the resultant is equal to e sin alpha divided by alpha by n is equal to na sin alpha divided by alpha. This is a n is a constant, a is a constant. Let me consider this value is another constant with a naught. Then r is equal to a naught sin alpha divided by alpha. This is the value of resultant amplitude due to a number of slits. As we know that I is equal to amplitude square. So I is equal to I naught square sin square alpha divided by alpha square. This equation which will explain the intensity. This equation will explain the intensity at point P. It is maximum or minimum. Or minimum. So the condition for the maxima and minima. So the condition for the maxima and minima for the Fraunhofer diffraction through a single slit, we have the primary conditions for the maxima and minima, and I is equal to a naught sin square alpha divided by alpha square. To find out the maxima and minima, let me differentiate I with alpha and put this is equal to 0. Then d by d alpha a naught sin alpha square divided by alpha alpha square is equal to 0. By the differentiation, we get the value alpha 4 a naught square, the alpha square as it is 2 sine alpha cos alpha minus the differentiation of lower term 2 alpha, upper term as it is this one. Let me cross multiply with this value, it becomes 0. Then we get a naught a naught alpha 2 and sin alpha is taking out from this bracket. Then it contain alpha cos alpha minus sin alpha. By this condition, we get the value of intensity for the minima and maxima. From the equation, we have two factors. One is this and the second is this, and the multiplication of two factor is equal to 0. Then either this value is equal to 0 or this whole value is equal to 0. Let me solve these terms one by one. Here we have two cases. The case 1 is a naught square 2 alpha sin alpha is equal to 0. Actually the a naught square is a finite integer, and it is a amplitude. Now either alpha 0 or sin alpha 0. Okay. Now sin alpha is equal to 0, then if alpha is equal to plus minus n lambda. Clear है? This value, and alpha is not equal to 0 because if alpha is equal to 0, then what will happen? Then sin alpha divided by alpha become indeterminate form. So the next point is alpha is equal to plus minus n lambda, where n is not equal to 0. So इसलिए n is equal to 1, 2, 3 and so on. from this we get the values as in the previous assumption. We assume alpha is equal to pi d sine theta divided by lambda. Okay, and here we have this is equal to this and is equal to plus minus n lambda. From this equation we can solve this equation. Here the d sine theta is equal to plus minus n lambda, and from this sine theta is equal to plus minus n lambda by d, where d is the slit width. Since the intensity becomes zero at intensity, where is the intensity become zero? When the sine alpha divided by alpha is equal to zero, then the intensity become zero. Then the intensity become zero. And the second point is the second point. This is this is equal to sine theta 1 equal to n is equal to 1 lambda by d plus minus for first minima. First minima. Similarly, we can write for the other minimas sine theta n in general case. Generally, this is equal to this. This is the case number 1. Let me discuss about the case number 2. The case 2 is we have alpha cos alpha minus sin alpha is equal to 0. From this we can get tan alpha equal to alpha, and to solve this equation we need to draw the curves where curve y1 is equal to alpha and the y2 is equal to tan alpha, and the intersection of curve will give the values of alpha. Here we consider the alphas. We plot the alpha for 0 plus minus 3 pi by 2 plus minus 5 pi by 2 plus minus 7 pi by 2 and so on. Let me draw these two curves. One, two, three, and so on. This is y and origin. This is the tangent line. This is again second tangent line and third. This represents the y is equal to tan alpha, y is equal to tan alpha, y is equal to tan alpha. Now, these values are this is 0, 3 pi by 2, 5 pi by 2, 7 pi by 2, and so on. This is the curve which y is equal to alpha. The point of intersection, this point of intersections will give the value of the roots of equation tan alpha into alpha. Now let me discuss about the intensity. Here alpha is equal to 0 corresponding to the central maxima, central maxima. Hence the central maxima of the intensity I is equal to A naught square sine square alpha divided by alpha square, and this can be written as A naught square sine alpha divided by alpha whole square. Let me put the limit alpha tends to 0, then limit alpha tends to 0 sine alpha divided by alpha is equal to 1, and we get the intensity is equal to A naught square. This is the intensity for central maxima. Central maxima. Let me move on the other maximum intensities in this equation. Let me put the values of alpha. A naught square sine alpha, and the value of alpha for this is 3 pi by 2. The next value for alpha is 3 pi by 2 to the whole square, and which is nearly equal to A naught square divided by 22 is equal to I naught 22. Similarly, for the next value, I is equal to A naught sine 5 pi by 2 divided by 5 pi by 2 whole square, and which is equal to A naught square divided by 61 is equal to A naught divided by 61. Similarly, for the third maxima, this is for first maxima, second maxima, central maxima, and third maxima. Third maxima is equal to this sine 7 pi divided by 2, 7 pi divided by 2 is equal to A naught square divided by 1 to 1 is equal to I naught. So the ratios of the maxima are maximum intensities of the first, second, and third maximas are 1 by 2, 22, 1 by 61, 1 by 2, 1, 2, and so on. In this way, we can see that the intensity of the all secondary maxima, secondary, tertiary, and further are decreasing continuously. Then we get a pattern in this way. This is central maxima, first maxima, second maxima, third, and so on the both sides. This is 0, this one is minus pi, pi, 2 pi, 3 pi, minus 2 pi, minus 3 pi, minus 4 pi, and the maxima are 3 pi by 2, 5 pi by 2, 7 pi by 2, like this, pi by 2, and 7 pi by 2.